Okay, so in our previous segments, we've been talking about what matter is. And matter makes up 4% of the universe. So imagine that. You look around you, you see tables, you see chairs, you see yourself. Everything is composed of atoms. Those atoms are composed of electrons that make a cloud that surrounds the nucleus. The nucleus, in turn, is made up of protons and neutrons. We now know that the protons and neutrons are going to be composed of quarks. So matter is going to be composed of quarks, and then you have to have these leptons as well in order to explain how this matter interacts. And that's only 4% of the universe. So now we want to talk about another 23% of the universe, and that is going to be dark matter. And so dark matter is going to be dark. It does not interact with any type of light. So light is an electromagnetic wave. And we said that it starts off with radio waves over here, and then infrared, and then visible light, the Roy G. Biv thing, and then ultraviolet X-rays, and then gamma rays. So all of those were different kinds of electromagnetic radiation. Dark matter has this property that when an electromagnetic wave hits it, nothing happens. So it doesn't, there's evidently nothing in dark matter that has energy levels that will react to the incoming light and make something jump up and down so that it will react with electromagnetic radiation. It just doesn't. So whatever dark matter is, it does not react with the electromagnetic radiation. But it does have mass. So dark matter has mass. And so it does cause gravity. It does cause the force of gravity. It does bend space and time just like conventional mass does. So what is the evidence for dark matter? Okay, one thing is that galaxies, some galaxies are spinning. So spiral galaxies, the spherical galaxies are spinning at a certain rate. And so we can predict how fast they should be rotating based on Newtonian mechanics. And so I'm going to show you how this can be done in the appendix of this particular lesson. So you don't need to know how it's actually done other than the fact that it's done. So by using Newtonian mechanics, we can predict the rate at which a galaxy should be spinning, and that in turn depends on the mass of the galaxy. So we have actually measured the rate at which galaxies are spinning by looking at them through our telescope and then by using a stopwatch. And so we've actually calculated how fast are they spinning. But then we've also calculated how fast they should be spinning based on their mass. And we find that there's a discrepancy. So when their speed is measured based on the Doppler effect using light, they're rotating too slowly. And so what this indicates is that these galaxies actually contain more mass than what we can see with our eyes. And so this missing mass is dark matter. So we think that surrounding galaxies is this dark halo of dark matter. And there's also dark matter in the galaxy itself. And all of this additional mass is what's making these galaxies rotate so slow. Okay, another thing that mass can do is it can bend space and time. So that here is, let's say that this is the Earth located here. Okay, now let's say that you've got a star that is located right there. And in between the Earth and the star is a very massive object. Now it could be a black hole, but what we're symbolizing here is that this is dark matter. So let's say that there's some dark matter that is in between Earth and the star. Now this star is emitting light in this direction, but it's also emitting light in this direction, and in this direction, and in this direction. So the star is emitting visible light in all directions. But because of the bending of space and time, this light that starts going in this direction is going to be bent by the gravity of this object, and it's going to cause it to curve around and then hit the Earth. And then light on this side is going to do the same thing. Now, we like to think that light travels in straight lines. So we don't see the light curving like this. What we see on Earth is we think that the light is traveling in a straight line, and so it's coming from these two objects over here and over here. So we see with our telescopes two stars, when in fact there is only one star. So this star is causing these two images of this star, and it's being caused by the gravity of this thing in between. So what could be causing the light to bend is dark matter. So that's another evidence for dark matter. All right, so what could dark matter be? So the first theory was it's a neutrino. So when a proton changes into a neutron, other particles are given off. So like for example, a positron, so it's going to be an electron that has a positive charge, is also going to be emitted. So that takes into account the positive charge. See, it's changing from positive charge to no charge. So in order to conserve electrical charge, another particle had to be emitted, and that would be the positron. But do you remember that we said that spin also has to be conserved? So if something is spinning before and then it breaks apart into multiple particles, when you add those spins together, it has to equal the original spin of the object. So let's say that this thing was spinning clockwise and the neutrino is spinning clockwise, but the electron is also spinning. It would be spinning in the opposite direction. So they would cancel each other out. So we need one more particle in order to balance the equation, and that's the neutrino. So a neutrino is a teeny tiny particle about the size of the electron, but it has no electrical charge, and it's going to account for the spin. So that when you add the spin of this plus the spin of this plus the spin of this, you get the spin of that thing there. So neutrinos are very, very small. Okay, they have a mass which is very, very small. But if you were to have enough of them, you would have a lot of mass. And so what they thought originally was that since stars, through nuclear fusion, convert hydrogen into helium, one of the other things that they produce is neutrinos. And so if you added together all the neutrinos in the universe, maybe that accounts for the mass of the dark matter. Well, then they came up with another theory, and they said that they were quarks, okay? But do you remember that there were the nucleons had 3 quarks in them, but then there were the hyperons that could have 5 quarks or 7 quarks or even more quarks. So they said that maybe what happens is that there are other particles in our universe that we can't see, we can't detect them using light, But since they're composed of quarks, they're massive, and so maybe that's what dark matter is. Okay, then a theory that came a little bit later is called axions. And so it's kind of complicated, but in high energy physics, there is a thing called the CP problem that says that it's a problem because neutrons do not have any electrical charge. Neutrons are neutral. But think about what's inside the neutron. So there, inside the neutron was a down, and an up quark, and each of those quarks have electrical charge. So theoretically, if you send light into a neutron, it should react to that light because the quarks that make up that neutron ought to react because they are electrical in nature. But they don't. And so we called this the CP problem. So they invented another particle called the axion. So the axion particle was hypothesized to be able to switch off the interaction between the neutrons and electricity, effectively solving the CP problem. All right. So anyway, that's what an axion is. And so since they said axions have mass, maybe that's what dark matter is. Now the latest theory as to what dark matter is it's a super partner. And we will discuss that in a later segment. So just keep that in mind, that super partners could be a candidate for what dark matter is. Okay, let's take a break, and when we come back, we're going to talk about what dark energy is.